Good morning. We'll get started today. We're just continuing along in the chapter 7 to 9 packets. If anybody has any specific questions, feel free to interject at any point this morning. But how many total domains and bonding domains does the sulfite ion have, SO3 2-? So when we're working out this structure here, we need to take into account the 6 valence electrons for sulfur, the 3 times 6 for oxygen, the 2 for the negative charge. That gives us a total of 26 valence electrons to distribute within the Lewis structure. And so that's how we know to start with essential sulfur, start with our 3 bonds to oxygen, lone pairs around the O's, just to make sure we see that that's our 24 electrons and that our 2 electrons left over, yet to be assigned, placed onto the central atom. And so once we put those 2 electrons onto the central atom, we could then consider formal charges, think about if we want to make multiple bonds. For the sake of this question, it almost doesn't matter though. We are satisfying the octet of sulfur, so this is one of the valid Lewis structures for the sulfite ion. I would take this to actually be the best Lewis structure, because if we take note of sulfur's should have 6, has 5, it's a +1 formal charge, but that's okay. The oxygens are all negative, that's okay too. That's a common formal charge we see for oxygen. If we tried to make a double bond, we could do that and minimize the magnitudes of formal charge, but we're expanding the octet, so we could get a Lewis structure that looks something like this. And somehow we have to picture resonance, delocalization taking place. It's kind of hard to actually imagine how that would take place because there's no good bonding model to show that, but nevertheless, that would be another one of the Lewis structures. If we think this is the Lewis structure, then we have to consider resonance over to here, resonance over to here. So the bonds are all going to be identical on this structure. But in terms of the question being asked here, how many total domains are there? If it's a double and 2 singles and a lone pair, that's the same as 3 singles and a lone pair in terms of the domains. So we have a total of 1, 2, 3 bonding domains, and then a total of 1 non-bonding domain. And that takes us to 4 total. So the geometry of this model should fit into a tetrahedral electron domain geometry. If we were asked for the geometry, we'd have our central sulfur, lone pair, oxygen, and then we'd be in a tetrahedral geometry. So 4 total domains, 3 of them are bonding. Next question, we'll go over a bunch of questions about electron domain geometry, then get into polarity versus, is the molecule polar or non-polar. So for PF3, we have a total of 26 as well. 5 plus 3 times 7, that's 26 valence electrons. So we're going to find ourselves in that same basic Lewis structure that we had for SO3 2-. So central phosphorus, fluorines. I'm going to go ahead and sketch this in the tetrahedral geometry to begin with. Lone pairs on the top face of the tetrahedral geometry. And so the electron domain geometry is tetrahedral. And then our molecular geometry name is going to be different because it's just what's the geometry for where the atoms are. And so this looks like a pyramid structure on top of a triangle, so we call it trigonal pyramidal. And you only go bipyramidal if there's 2 pyramids. There's only a single pyramid here. So think, are there 2 pyramids in the structure or just 1? There's only 1, so this is just a single pyramid. And then is this molecule polar or non-polar? Well, certainly the bonds are polar. Fluorine's really electronegative. Phosphorus is not fluorine, so we're going to have an electronegative bond. Fluorines are going to go partial negative. And phosphorus has a big positive charge that's not balanced out on the opposite side of that molecule. So this would be a polar molecule. What about IF5? Well, each of them have 7 valence electrons. There's 7 atoms. That's 42 total. So we should have a central iodine. And I'm going to go ahead and kind of sketch this in one of its geometries, or in its molecular geometry. But the key is we have a lone pair on iodine because we have 5 electrons around each of the we have 3 electron pairs around each of the fluorines. That's 8 electrons around each F. There's 5 Fs. That's 40 of our electrons, leaving 2 electrons left over that we put onto the central atom here. And so that gives us a total of 6 domains. 6 domains fits into the electron domain geometry of octahedral. So we have the octahedral electron domain geometry. And then since we don't have a bonding domain in one of the spots, we have to change the name of the molecular geometry. We're looking for the geometry name of this structure here. And there's a square in the center. So octahedral has a square structure like this, an atom straight down. So we get a single pyramid, but about a square. So we call this square and single pyramid, so square pyramidal. And do we expect that molecule to be polar or non-polar? Well, if we had something like SF6, if we had a fluorine atom where the lone pair is, then that would have kicked the structure into non-polar. But because we have that lone pair in place here, this allows us to develop all these fluorines pulling electrons away from iodine, creating a partial negative on one side of the molecule that's not balanced on the opposite side. So we have, again, like PF3, a polar molecule. So we need there to be symmetry. We need the like dipoles to be opposite each other and cancel across the whole structure, and so we almost had it. So we had 2 bonds kind of opposite each other, and then one without a bond opposite of it. So we end up with a polar molecule. Now xenon F4, let's take a look at this one. That'll be 8 plus 4 times 7. That's 36 valence electrons. So central xenon, 4 fluorines. And then our lone pairs are going to be in this geometry here. How do I know I have 2 lone pairs? Well, if I count my electrons, I have 3 pairs around each F. 4 Fs, that's 32 electrons, leaving 4 behind. So those are the 4 electrons here and here. And so we have 2 lone pairs sticking straight out of the xenon atom in and out of the page. And then we have the 4 xenon F bonds here, perfectly 90-degree bond angles, perfect square planar. So this geometry still is in the octahedral domain, but it's square planar. Anytime we say a geometry is planar, we mean the entire molecule exists in one single plane. And those lone pairs, if you imagine lone pairs usually try to compress bond angles, well, you have a lone pair on either side. So we're bonds like this. We have lone pairs above and below us. We can't really adjust in and out of the plane, so we stay perfectly in plane, perfectly 90 degrees. And these dipoles now are exactly opposite each other and cancel out. So these geometries here, the geometry of this molecule allows those bond dipoles to perfectly cancel each other out. We therefore end up with a nonpolar molecule. Now, if we go back to like linear CO2, that's nonpolar. If you go to trigonal planar, BF3, that's nonpolar. If you go to CF4, so CF4, looking like tetrahedral, that's nonpolar. So anytime you're in the main name, so if you're in linear, trigonal planar, tetrahedral, trigonal bipyramidal, or octahedral, the same atom in all the positions, then that molecule has to be nonpolar. And then we also then see there's 2 other geometries that are like subgeometries, where you have lone pairs in the structure. Those would be xenon F2. If you remember, if you have linear within trigonal bipyramidal, that was nonpolar. And then we see here like xenon F4, we have nonpolar within square planar. So then if we think about going through the range of possibilities of if we're bent within trigonal planar, that's polar. If we're bent or trigonal pyramidal, like within tetrahedral, like PF3 or water, obviously those are going to be polar. If we're within the trigonal bipyramidal and we're either that seesaw or T-shaped geometry, those will be polar as well, SF4. We see here we have a lone pair on sulfur, 4 bonds. So this is going to fit into that trigonal bipyramidal domain because we have 5 total domains. So with 5 total domains, we're fitting into trigonal bipyramidal. So central sulfur. Think about this geometry here. Put a lone pair in one of the spots. Put fluorines in the others. And then just try to think, well, what shape is that? That's like a teeter-totter. That's a seesaw. So we call this the seesaw geometry. And then this structure here has fluorines opposite, almost canceling, but then these dipoles here don't cancel. We have a net dipole moment pointing towards the fluorines. We have a positive charge on sulfur that's not balanced on the opposite end of the molecule. And the reason why I'm saying those dipoles like here and here don't perfectly cancel is they're really bent a little bit. So they're not perfectly 180, they're like 174 because of the lone pair pressing these bond angles closer together. So we end up with a polar molecule. Okay, so hopefully you have a few ways to try to determine if a molecule is polar. There's the brute memorization way, which is just, again, like if you're in the base geometry, like linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, it has to be nonpolar if you have the same atom in every spot. And then likewise, if you're linear within xenon F2, within trigonal bipyramidal, if you're square planar, you're also in this nonpolar geometry. Let's look at this question here. So the really interesting thing with the molecules on this page is that cisplatin, which is this structure here, that cisplatin is one of the first developed cancer-fighting drugs. It's still used today. And if you compare it with an isomer of it's called transplatin, where it has the two chlorines, instead of adjacent to each other, it has them opposite each other. And so that's transplatin. And it doesn't particularly have, I don't know if it has a negative interaction in the body, but it certainly doesn't fight cancer in the same way that the cisplatin molecule does. Now, interestingly, the molecules really are square planar. And the reason why I wanted to have this slide here is not so much that I think they're going to get really tricky with polarity questions, but sometimes we show you a structure and you have to interpret, is the geometry really truly square planar? Like if I were to write F4 this way, then is it really 90-degree bond angles? The answer is no. This molecule here is really tetrahedral. So we might sketch it flat just because it's convenient, but really have to picture that it looks more like a tetrahedral molecule. If we're picturing, well, change two of these to like hydrogens instead of fluorines, then we're changing two of these here to hydrogens. And then all of a sudden within this geometry here, this looks like a polar molecule because we have the fluorines not opposite two other fluorines. And then if I sketch this Lewis structure equivalently like this, if I put the molecule like this, you might be tricked into thinking that this is nonpolar because the two fluorines look opposite, the two hydrogens look opposite. Why wouldn't this be nonpolar? And the answer is because that's not the real molecular geometry. The real molecular geometry looks more like this, and the molecule's polar. Well, in the case of the platinum compounds, we're telling you that they're really truly square planar, meaning these bond angles here are perfectly 90 degrees. And so the structure here, these dipoles between platinum and nitrogen perfectly cancel, and the dipoles between the two chlorines cancel. So whatever the poling strength is here cancels out, whatever the strength is here cancels out, the net molecule ends up being nonpolar. And then over here, we end up with a polar molecule because we get a different dipole moment. Imagine this dipole, let's just say it's bigger. And so let's imagine this dipole is smaller. Whether or not it's in that true order, but imagine the two dipoles are just different. We get a net dipole different this direction than the opposite direction. And the cisplatin molecule, we end up with a polar molecule. So perhaps cisplatin being polar gives it a different property in the body than the molecule that's nonpolar. Usually polar molecules are stickier to other polar molecules or more, there might be a certain enzyme that needs a certain polarity in order for there to be some kind of molecule-drug interaction that we don't get with the transplatin molecule. But the key to me is, if I see a Lewis structure, I have to interpret the shape. I have to then think, am I told in the problem something about the geometry, or do I have to interpret what I know from molecular geometry? For example, if I show you water, it looks like this. Do you see how we're kind of like, if I say, is this polar or nonpolar? Do you see how I'm kind of tricking you almost into saying it's nonpolar, even though it's not nonpolar? The real structure is bent. So we have to think this bond angle here, is it really 180 degrees? It's not. So if we give you a Lewis structure, just know that unless we tell you that that's the real shape of the molecule, you have to interpret the three-dimensional shape. We do this also, and we'll see a couple examples in a moment, where we'll sketch molecules like, like this. And these molecules, you'll see this in OChem too, that's not the molecular geometry. We're just sketching it that way because it's easy to do. It's hard to make the 3D sketches of these molecules for our lecture notes, so we just write them flat, and we have to then interpret, oh, this is really tetrahedral. Those bond angles are truly 109.5. We could sketch it if we had to, but we're going to interpret the bond angles based off of number of domains. If it's 4, it's tetrahedral. If it's 3, it's trigonal planar. If it's 2, it's linear, etc. So this here is tetrahedral base geometry, so that bond would be bent closer to 109.5. So therefore, this molecule would be polar. So I just want to use this slide to kind of show you a couple general types of ways we tend to ask polarity questions. Like, I don't think we'll go exotic with our molecules. I think we'll keep it relatively simple in the exam. But if we show you Lewis structures, just be sure to interpret the actual 3D molecular shapes and then assess for those shapes, is the molecule polar or nonpolar. Let's get into some of the later chapter, like I guess it's more middle, but later in our coverage, because we're only going through section 9.6 on the exam, but this is from like section 9.6, I believe. How many total sigma and pi bonds does the molecule below contain? A couple of questions about bond angles, what they're closest to, and then something about delocalization. So let's take the first question up top first, the sigma versus the pi bonds. Well, let's indicate first, let's just sort of circle out the double bonds. So I just want to take note of these double bonds here, and then there's these two here as well. And so for all those bonds thus far that I've circled, we can imagine that we're going to get some kind of overlap to make a sigma bond and some other type of overlap to make a pi bond. So each of these bonds should be a sigma plus a pi bond. I don't know if we have to write this in every single case, but I'm just going to write it in 5 times because why not? But it's just each of those bonds is some type of sigma overlap and some type of pi overlap. We could talk about what makes the overlap in a minute, but for now, let's just take the sum total that so far I have 5 sigma bonds and I have 5 pi bonds, just from taking note of the 5 double bonds. That a double bond should be a sigma and a pi, and if we had a triple, which we don't in this structure, a triple bond would be a sigma plus 2 pi. And then all of our single bonds are just a sigma. So all the single bonds in the structure would just be a sigma bond. And so I'm going to start here. So I'm just going to write in sigma here every time I see a single bond, and I'm going to count up all my sigmas. I think that's all of them. So that would be 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Missed one. I know there's 16 because I did this a couple. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 16. Sometimes it's helpful if you do it twice if you're not sure. I knew I did this for the key, so I knew that there were 16. When I got 15, I knew I missed one. But we're just counting the single bonds as our sigmas and then adding these up to 21 total sigma plus 5 pi. So again, this question here is just getting at, do we get the difference between single bonds or sigma bonds and then double bonds or a sigma plus a pi? Now let's take apart, a couple of the bonds. Like, let's take a look at one of these bonds here and try to say, well, what is the sigma? The sigma is depicting that each of the central atoms for this carbon here should be an sp2. Why sp2? Well, it's trigonal planar. That carbon that I've indicated here has 3 bonding domains, so it's trigonal planar, and its geometry, so its bonding model has to have 3 orbitals, so therefore sp2, and then it leaves behind a p orbital. So the extra p, there's 3 p orbitals. The third p orbital wasn't hybridized. It makes the pi bond. So our sigma-sigma bond, like our sp2-sp2 overlap between the 2 adjacent carbons, this is our sigma bond. And then the p orbitals that are left over and unhybridized, each of the carbons has a p orbital sticking straight out of it that overlap in a plane. It's hard to sketch the structure. Let me try with green. This probably won't look great, but imagine you have a p orbital sticking straight out of the page, and then that p orbital overlaps to make that pi bond. So you get the p-p overlap. You can call it the 2p because it's a carbon atom and its biggest orbital is a 2p. That makes up the pi bond. And so the leftover p orbital from the hybridization process overlaps to make the pi bonds. And so every time we have a double bond, it's some type of sigma-sigma, or the sp2-sp2 or hybrid orbital overlap to make the sigma bond, and then that leftover p orbital makes the pi bond. Okay, let's think about a couple bond angles here. I know the page is kind of littered already with a bunch of writing, but let's look at bond angle 1. So bond angle 1 is about a central carbon. It's a bond angle of that central carbon. It has 3 total domains. So we should expect angle 1 to be closest to 120 degrees because it's trigonal planar. So it's just looking at the geometry based on total number of domains. Angle number 3, let's do it next. We have 1, 2, 3. That looks like a double bond, so let me undo that. So we have 3 domains here, or excuse me, 4 domains. We have 2 non-bonding, 2 bonding domains. So this oxygen here would be tetrahedral because it has 4 domains. If we're talking hybridization, it would be an sp3, and its bond angle should be closest to 109.5 degrees. You can even predict it's probably a little less than 109.5 due to the lone pair interactions. But if you're guessing close to 109.5, that's what we'd be looking for in a question like this. And then our bond angle for 2, we're back to an sp2 trigonal planar geometry, so that should be close to 120 degrees. If you're saying, I actually predict it to be a little bit greater than 120 because it's a double bond, single bond, and I know the 2 single bonds will get a little closer together, that's great. Questions like this, we're usually not trying to test too many aspects at once. Big molecules, we're usually just looking, is it closest to 120, closest to 109, closest to 120. If we do kind of want to nitpick between like bond angle, say 3, and let's say bond angle 4, this bond angle here for 4, about this carbon, that's also tetrahedral. It's going to be almost perfectly 109.5 degrees. You could expect 3 would be less than 4 just because 3 has those lone pair interactions. So you could get a little bit into the finer detail of geometries. You could probably predict that 2 should be a little bit greater than 1 just due to the double bond, single bond interactions. Now, you may be looking at the question of the 120 on angle 1 and saying, well, what about the double over single there? But this has to do with that last question of delocalization. These double bonds could all move over to here, and we actually have resonance with that pi bond system. Within that ring system, we actually get a Lewis structure, and we get an equivalent bond that's formed. So all these bonds here in the middle would be exactly the same, just like a benzene ring. So which double bonds are delocalized? Again, hard to write, but it's these ones here that I'm circling in yellow in terms of their bonding nature. So it's those double bonds there that are delocalized, meaning that there's one other Lewis structure we can sketch. The real molecule is the average of those Lewis structures. So we really don't have a double bond, single bond. If we're looking, I know this is really littered, I could erase, I don't know if it helps, but if you look at these bonds here, it's not really single versus double, they're really both 3 halves bonds in the same. And so that means that the bond angle for 1 will be pretty much exactly 120. And then if we compare that to angle 2, 2 should be a little bit greater because of that double bond, single bond interaction. And we don't get delocalization for the double bonds between the C and the O. Those are what we call localized bonds. Those are bonds exactly where you think they are. They're not spreading out within any other kind of Lewis structure. Okay, so a lot of questions you might see from this on the test just get at sigma versus pi bonding, describing bonds. There's another question or 2 on this topic, so we'll come back to the topic of describing bonds in a minute. You also can look at delocalization a little bit or predicting bond angles. We can use hybrid or valence bond theory to describe molecules. We just kind of go back to their basic geometry. So if we're looking at CCl4, now maybe let me use easier to see color. If we're counting our electrons, we get 32 total. You might have this Lewis structure memorized already. We've sketched it a bunch of times, but it's just the 4 carbon-chlorine bonds. So we use all 32 electrons done left over for the central atom. So 4 equivalent bonds between carbon and chlorine. And so this should be a tetrahedral carbon. Even though I drew it flat, it's really tetrahedral, 109.5 degree bond angles. Because it's tetrahedral means its description in hybrid orbital theory would be sp3. So I need 4 orbitals to get the 4 hybrid orbitals I need. So I need 4 hybrid orbitals. And so to get 4 hybrid orbitals, I need to start with that hybridization set for carbon using all 4 of its atomic orbitals. NH3, same idea. NH3 has a lone pair on hydrogen. And so then we get 4 domains here too. So that should also be tetrahedral, should also be sp3 description. Now what this means is like if we're describing the carbon-chlorine bond in CCl4, I describe this bond here as sp3, and then what's the largest bond of chlorine? It has, chlorine is a 3s2, spin paired 3p5. So So we have this one unpaired electron that pairs up with the carbon unpaired electron in the sp3 orbital, and so we call it sp3 3p overlap. So you're getting the overlap that looks kind of like this from that p orbital, and then that hybrid orbital overlap. And so of course that's a sigma bond described by the sp3 3p overlap. NH3 is going to have sigma bonding as well. The sigma bond here will be made about from the nitrogen, sp3, but now just with the 1s of hydrogen. So the 1s unpaired electron pairs up with the electron in the hybrid orbital of NH3. And again, looks kind of just like this. What about HCN? I don't know if you know the Lewis structure right off the bat. If you don't, just go back to the basic rules and kind of start with the lone pair on nitrogen like this. By our basic rules, give the non-central atoms their octet with lone pairs. That's all 10 electrons. Think about the formal charge of the central atom. Think about if it has room for more electrons, i.e. if it has its octet filled or not. So it has an open octet. So we make a double bond, reduce this formal charge down to plus. So we've lost that lone pair here. Let's lose this lone pair here, make a triple bond. And so we end up with HC triple bond to N lone pair on nitrogen as our best geometry. And then the central carbon here has 2 total domains. It doesn't matter that it's triple single. This is still 2 total domains, still perfectly 180 degrees. And then we'd be describing the bonds here as the central carbon being sp hybridized. So I get sp 1s overlap between the CH bond, so the CH sigma, sp 1s overlap. And then between the nitrogen, if you picture nitrogen being sp hybridized as well, because it has 2 domains. So I have 2 sp orbitals for nitrogen, so I get sp overlap for my sigma. And then pi bond number 1 is this p orbital, that p orbital. And then pi orbital number 2 is this p orbital, that p orbital. So I get 2 sets of p orbitals overlapping with each other because I have 2 unhybridized p orbitals in and out of the page and up and down in the page. So I get 2 different pi bonds overlapping with each other within this molecule here. And again, with a triple bond, you should have been thinking sigma plus 2 pi as well. Okay, so we can describe these molecules with these bonding theories. Now CLF actually is a little bit simpler. It just goes back to just valence bond theory, which is just saying, well, chlorine's largest orbital is a 3p, which has 1 unpaired electron. Fluorine's largest would just be a 2p. Let me put fluorine a little closer since it's smaller. So we have the chlorine 2p, which has an unpaired electron, and then those just pair up within a sigma bond. So my sigma bond here would be 3p, 2p overlap. So the 3p of chlorine with the 2p of fluorine. So when, if you go back to like HF, HCl, Cl2, F2 molecules that are simple like that, we don't need any hybridization set for those. Once we get to things like NH3, CH4, water, we can then use a hybridization theory for the central atom, and then think usually about the outer atoms if they're O atoms or halogens just by their, hydrogens being the 1s, fluorine's like a 2p, chlorine's a 3p to get our overlap. What molecule has this particular geometry? Well, what is the name of that geometry might be your first thought. You see how it looks like a T, so that's the T-shaped geometry. We get a T-shaped geometry whenever we have a lone pair here and then a lone pair here. So we need there to be 5 total domains for this molecule to get this geometry. 3 of them have to be bonding, and then 2 have to be non-bonding. And so I'm looking for a molecule that has 3 bonding domains, so it has to pair up with 3 things. So that's going to roll out SO2 and SF2 right off the bat because those only have 2 bonding partners, so those are only going to have 2 maximum bonding domains. And then CF4 can also be rolled out because it's going to have 4 bonding domains. So we know CF4 should also be tetrahedral, so tetrahedral domain, tetrahedral molecular geometry. SF2, if you're not sure, just do the Lewis structure later, but you get 2 lone pairs. This ends up being bent on the tetrahedral domain. So tetrahedral domain, bent molecular geometry. SO2 looks like lone pair, bonds to O like this, and this ends up being bent within trigonal planar. just hopefully for a quick review of some Lewis structures. Again, if you're stuck in the Lewis structure, go back to the Lewis structure that you would sketch by the rules and see that you should end up with like a lone pair on sulfur, therefore into 3 total domains. So 1, 2, 3 for trigonal planar electron domain geometry. BRF3 should have 2 lone pairs on bromine, 7 times 4 total, 28 electrons, so central bromine, 3 fluorines, lone pairs around the Fs. That's 24 of the electrons, doing the same thing around each of the Fs, leaving 4 electrons behind, fitting into that geometry of T-shaped. Okay, so if we show you a picture, just interpret what is the shape of the geometry and the molecule that's shown. You know, we could show you any of the geometries. We could show you a bent geometry, we can show you trigonal, pyramidal, trigonal planar, etc. And you're just looking for the molecule consistent with that geometry. And then which molecule above has an sp2 hybridized central atom will be the trigonal planar. So this has to be trigonal planar. So that would be this guy here. The SO2 would be trigonal planar. SF2, CF4 are both tetrahedral, so these would be both sp3 hybrids within hybrid orbital theory for the central atoms. I think we're down to one last question from our packet, and that is to imagine the pi bond between 2 carbons in ethylene C2H4. Now, you may or may not know the Lewis structure right off the bat. Let's imagine you don't know the Lewis structure right off the bat. So, and probably if we were to ask a question like this, we would probably give you the Lewis structure. But C2H4 would be for the carbons, 2 times 4, plus the 4 hydrogens, 4 times 1. So that's 12 total electrons. So far, I have 10 distributed. If I put 1 on each carbon, we can then be like, well, why don't we make the double bond? So it's just a double bond. Another thing you can think is if we give you this Lewis structure, then let's try to interpret the question that these 2 carbons should be sp2 hybridized, and we should know that you get a sigma plus a pi for the double bond, and then these bonds here should be sigmas. If we were asked a total sigma pi question like that larger molecule, we'd have 5 sigma plus the 1 pi. We usually are testing if you know that the double bond is the pi and a sigma, because either you might think it's 2 pi bonds for a double, but it's not, it's a sigma and a pi, or you might think it's just 1 pi bond, but it's a sigma and a pi. And the sigma is the sp2 overlap, that's our sigma bond. And then the p orbital overlap. Again, it's hard to sketch the p orbital overlap. One of the ways you could do that is you can maybe put the hydrogens as if they're coming in and out of the page. So if we rotate this molecule to look like this, where our hydrogens are coming out of the page, then we can picture this p orbital here that overlaps in the plane of our paper. And so that 2p overlap, the unhybridized p orbital overlap, is where we get the pi bond. So the pi bond is described by the p orbital overlap. So the pi bond between the 2 carbons in ethylene is formed from what type of overlap? It's the overlapping of the 2p orbitals, the two p orbitals. And then the 2 sp2 orbitals, this makes up the sigma bond. sp2 and sp2 orbitals, like an sp2, like this orbital here, that I'm sketching here, do you see how it doesn't overlap with the sigma orbitals? Sigma orbitals are here, here, and here. They're not in the same plane as each other. They can't interact. So we don't get any interaction between these orbitals. And then the 2s orbitals are hybridized in with the p orbitals to make the sp2 hybrid. So we don't get just the pure s orbitals overlapping with each other within hybrid orbital theory. Okay, so quick review. Any final last questions I could take, if there are any? Make sure to look at the practice test. Make sure if you're stuck on any particular topic, try to review it. Look in the book, look for sample exercises, practice exercises, look for either like a daily quiz, questions on that particular topic. You can also go make AI quizzes. I don't know if you guys have been making more of those throughout this semester, but AI is not too bad at making you a practice quiz on selected topics. If you just tell it, make me a quiz based on general chemistry on XYZ topics, it should throw something fairly decent together. Okay, so with that, and I do hope that little bit of coverage into the last 2 sections of chapter 9 could help solidify a few aspects that we're talking about here in the early parts of chapter 9. The material from these sections will be covered on the final, not on the upcoming midterm. But one of the thoughts that we there's I think two main thoughts that we'll have on why we're going to still talk about bonding models, because it seems like we were almost done. Why are we still going to talk about a couple, or almost like a new bonding model? We're going to call this bonding model molecular orbital theory, but there's 2 types of things that we haven't really been able to describe yet. One would be, well, what happens when 2 heliums interact with each other? If we're picturing 2 heliums, you have like the idea of 2 spin paired electrons trying to pair up. Or what if you took like something that looks like helium or something like hydrogen, like ion? What if you took like an H- ion? So hydride would look like helium. It has that helium configuration. What if you allowed that to interact with like an H atom? Would there be any type of bond overlap between these types of orbitals here? Within our bonding models, you might expect that the 2 heliums shouldn't really be expected to interact with each other because they don't really, like they're both already spin filled. Like we are usually talking about unpaired electrons pairing up with another unpaired electron. Like a lot of our bonding models from hybrid theory, valence bond theory, kind of involve there being like a 2p or a 3p orbital with 1 electron in it overlapping with another such orbital that has 1 electron in it. Then they overlap together and then they fill their orbital shells and we're good. Well, what if the orbitals are already filled? Can they interact with each other? I don't think valence bond theory addresses that question. That's going to lead us into MO theory. So molecular orbital theory just basically says the same idea, that we have 2 s orbitals between, say, 2 hydrogens, and they can interact with each other to make a bonding molecular orbital. And this is the same type of overlap we were thinking within valence bond theory. So we get the overlapping of orbitals to make now what we call a sigma 1s orbital, and that's just more or less the same type of bonding description we would have had previously. So a sigma bond, single type bond between the 1s orbitals. But then we also get, well, there should be a constructive versus deconstructive interference pattern. We get also an antibonding orbital. So the antibonding orbital just says, however much this goes down in energy, this has to at least go up in energy by at least x, if not even more energy upward than we went downward in terms of the stability. It means if we're making an orbital stable by bonding, we have to then destabilize something else. We call that the antibonding orbital. Well, the good news for hydrogen is it just has 1 electron in each of these orbitals, so we're only putting 2 electrons into this, and we're putting 0 electrons up here for H2. So H2 is really good. It's putting 2 electrons into the most stabilized orbital, none of the electrons into the antibonding orbital. Well, if you're then picturing, I think it's on the next slide, if you're picturing helium, 2 helium atoms trying to interact in the same fashion, you can have, okay, now we have the same idea, but 2 spin paired electrons. Hydrogen had its electrons perfect, where we had unpaired electrons that could pair up their spins together. We're thinking spin up, spin down combination into the orbital so that we're still satisfying the Pauli exclusion principle into these orbitals as well. But perfectly for H2, no electrons have to go into that destabilized antibonding orbital. In the case of helium-2, if it were to make a bond, it would have to put 2 electrons into the sigma 1s, but then 2 electrons into that destabilized sigma star, the antibonding orbital. So the antibonding orbital would have to take 2 electrons for helium-2. Now, the answer is there's no net stability now. There's no net stability between making the bond because the energy that we had obtained going down was countered by going up, and then it has to go up by a value that's actually greater than x. So the amount that you go up has to be equal to or greater than the energy that we went downward. So meaning it's just a physics problem. If we go down by like minus 100, we have to go up by at least plus 100, if not greater. And so there's going to be no net stability for helium-2 to form, therefore it ends up being unstable. Now, one way we can see it's unstable is if we go to calculate its bond order. The bond order, let's do it for hydrogen first to see kind of a description. The bond order is just what we've been thinking about all along. We were thinking about this a little bit by calling bonds like 4/3 or 3/2, double bonds 2, single bonds 1. Our bond order is the net pairs of electrons shared between 2 atoms. And so our bond order can be calculated by taking 1/2 times the number of bonding electrons minus and this is total number of bonding electrons, and then minus the number of anti-bonding electrons. And so we have 2 bonding electrons, we have 0 anti-bonding electrons, and then we're just cutting it in half to make it a pair. So it's like how many electron pairs are there. And so we have a bond order of 1 for hydrogen, which is what we expect. It's a single bond. So the meaning of bond order of 1 is it's just a single bond. And that's exactly what we would expect. Of course, hydrogen has just the single bond linking the 2 atoms together. Then in the case of helium-2, we wouldn't expect there to be a bond between 2 heliums, between the noble gases. And we see that the bond order here would be a half 2 bonding electrons minus 2 anti-bonding electrons. And of course, that's equal to 0. And so that means that there's no stable bond. So we get no bond that forms between 2 helium atoms in the way that forms between 2 H atoms. And again, I think we could have predicted that. I think valence bond theory would say, yeah, we say that too, because we're kind of relying on there being unpaired electrons. Well, what if you took something weird like H2 with a minus charge? What if you said, well, what if you had H2 with an overall negative charge, where you're adding 1 electron to the picture, and so that might be the thought of having H minus plus an H atom. So let's make an H minus ion. The left side doesn't matter as much as what's in the middle. The left side is just, okay, I take an H minus and an H, overlap them to make the H2 minus in the middle. So I'm trying to put H2 minus in the middle, and I'm just putting 1 more electron here. And so the next spot to put electrons is in that sigma star orbital. So our bond order for this molecule here would be 1/2, 2 bonding minus 1 anti-bonding for half a bond. And you can have half a bond. That means that this ion would actually be stable, probably not stable enough to exist and ship and pair up with, things like, potassium ions, but this is something that you can maybe get to form in some type of an experiment where you can form this maybe in the gas phase or at low temperatures and study it, and it would have some stability where you could create it and collect some of its properties before it decomposed into something else. And so this would be, anything with a bond order other than 0 would be stable enough to exist at least for some short period of time. And so we get this bond order of 1/2 here for that molecule. And so we get that within our molecular orbital theory. Now, one other thing that and I do think this is the primary reason why we even are talking about MO theory, is that oxygen actually doesn't quite fit into being correctly described in any of the models we've discussed thus far. If I look at O2, and I'm picturing oxygen in its Lewis structure here, and I think I've mentioned this before, that there's something peculiar about O2, and that is it has unpaired electrons. Like if you're thinking about hybrid orbital theory, you'd probably be thinking, well, okay, these are just in sp2 orbitals, this is an sp2, that's an sp2, and so you're probably picturing, sp2 orbitals that are all kind of like, electron spin paired, and then we have the p that's unpaired that pairs up with the other p that's unpaired to make the pi bond. So within hybrid orbital theory, or within the Lewis structure, it doesn't look like there should be any unpaired electrons within this molecule. Well, it turns out O2 actually has 2 unpaired electrons. Now, I'm not a rocket scientist or anything, but I think oxygen having unpaired electrons makes it really important to be able to be accepted by hemoglobin and have the properties it has. If somehow oxygen molecularly didn't have those unpaired electrons, I bet it would be a little bit more like nitrogen, a little bit more in the case of not really reacting with things. So oxygen having these unpaired electrons seems like it would be pretty important towards its properties of being able to be grabbed a hold of by objects in the body and then pumped around, used, and then recycled in the form of CO2 and then expelled, etc. So these unpaired electrons have to be important towards the understanding of the molecule. Where do they come from? Why does O2 have these unpaired electrons? Well, that's going to lead us to a bonding model or a theory that shows, let's try to find a theory that shows where these unpaired electrons are so that we can understand why this molecule has these unpaired electrons. So what that kind of means is that somewhere along the way, these electrons are actually paired together in the same order, which we're going to have to find a model too that doesn't just violate the Pauli exclusion principle. We don't want to just say, oh, there's some orbital that just for whatever reason puts 2 electrons spin up. That's not going to be the answer either. We have to still think about satisfying the Pauli exclusion principle along the way. So let's try to see if we can put a bonding model together that shows O2 is paramagnetic, meaning it has at least 1. It's going to have 2 precise unpaired electrons. A molecule we call it to be diamagnetic if it has all of its electrons spin paired. Most molecules that are neutral, like CH4, water, methane, CH4, ethanol, those usually are diamagnetic. All the electrons are spin paired. So in most of our Lewis structures we've shown you so far within hybrid theory, you come up with a beautiful prediction that works out really well and supports those structures. And it's really just O2 that kind of stands out as being peculiar. So let's build up the idea of MO theory, kind of piecemeal together a little bit from, let's try to go from hydrogen, helium to lithium and diberyllium. And so lithium, like hydrogen, has a 2s1 outer configuration, like it's an ns1 configuration. Now, the orbitals that are in the 1s are smaller. So the 1s orbitals aren't going to interact with other 1s orbitals as much. So you're probably not going to get as much minus x and plus x character. In fact, soon we'll not even talk about the inner core orbitals at all. We'll just focus on the outer valence shell orbitals. But the minus x and plus x here, this x is going to go down by more because the 2s orbital is just larger. So you're going to get better overlap of the larger valence shell orbitals. And so this plus x, this might go down by, say, minus 10. This might go down by minus 100, just in relative scale. So minus x is probably dropping by about 10 times as much, if not more, for the 2s orbitals. But we get the same idea that the electrons, we're showing them in the same direction here, but that just means the electrons are going to be spinning, and then when they form the orbitals, they're going to have to then make sure that they pair up and have opposite spins as each other. So maybe the two electrons are spinning with the same spin, but when they make the bond, they have to pair up their spins together, one up, one down. And then we end up with this sigma 2s2 configuration. So if you're going with the full configuration here, bonding, anti-bonding orbital, those cancel out, so those no net bond here. We have a net single bond. So our bond order for lithium-2 would be equal to 1/2, 4 total bonding electrons, 2 anti-bonding electrons, so that's a single bond. So let's just, not boron, this is lithium making a single bond. Now, something complicated for lithium is it's not going to exist as a gaseous molecule like H2 does for reasons that are complicated. You can imagine that lithium-2, because it doesn't hold on to its electron as strongly, ends up forming like bonds with another lithium. So like two lithium-2s can interact with each other in two ways that two H2s don't interact with each other. Because hydrogen, it really wants to hold on to those electrons or maybe share it with one partner. Lithium is going to end up forming a solid structure that we're not going to talk about too much. We're just trying to think about, for diatomic molecules, what would their diagrams look like. Let's contrast this on this slide with diberyllium. So if we're comparing lithium-2 with diberyllium, so just the next element on the periodic table, diberyllium just has 2 more electrons. It's kind of like the helium-2 example, where it's going to have to put 2 electrons into an antibonding orbital. So diberyllium is not going to exist with a stable bond. So diberyllium's bond order would be equal to 1/2, and then 4 minus 4 for 0. So this is unstable. So 2 berylliums are not going to interact with each other in the way that 2 lithiums do. That doesn't mean that beryllium is not going to form a solid together. It's going to find some other way to interact its orbitals together that we're not going to talk about. But just the idea here is just trying to think about how these orbitals interact. Lithium-2, beryllium-2, very much like hydrogen and helium, diatomic molecules. And let's contrast, now let's bridge this into the next group of elements, that being, or compounds, boron-2 through neon-2. And this really is going to get into the heart of the matter, because we're going to get in this group, O2 and N2 and molecules like that. And so the difference here is we're seeing, okay, our 2s orbitals, now we're going to ignore the 1s. So the 2s orbitals closer to the nucleus. So we have s orbitals interacting and then p orbitals interacting on these atoms. And the p orbitals are either aligned directly at each other or they are planar relative to each other. So we're going to get 2 different types of interactions between the p orbitals. And so our s orbitals interact as they did before. So we get the s orbitals overlapping down and up to make our sigma bonding, sigma star anti-bonding orbital between the 2s orbitals. And then you would probably expect the 2 p orbitals that are sticking straight at each other to overlap the best between the 2 p orbitals, because they're overlapping each other really well. And so you can imagine you get your sigma 2p, that's this end-on-end overlap here. So you get a strong bonding orbital and anti-bonding orbital. So however much this goes down, this is going up by at least that much. And so we're going up in terms of the sigma star 2p for our highest orbital on the page. And then our pi set is the pi bonds. And now the hybrid orbital theory helps us understand that these orbitals here are going to interact through planar orbitals. And so this is our bonding orbital, and then this is the anti-bonding orbital. And so we're putting the electrons making the bond, and the anti-bonding orbital is trying to break the bond. So the idea, if we go back to hydrogen and helium for a minute. So hydrogen and helium, it's like the electrons here, this is like constructive interference. When we put the electrons between the nuclei, think of in physics how we would call it constructive interference. And if two electrons are here, the other two electrons are over here, that's like deconstructive interference. And so you can think of the constructively interfering waves making the bond, the deconstructively interfering waves making the anti-bond. And so if we're trying to pull the atoms together with the bonding orbital, the anti-bonding orbital is trying to do the opposite. But within a molecule, we're going to see that you can have bonding and anti-bonding orbitals, that's okay. The net bond has to then be made by the larger orbitals. And so we have a p orbital, like if we just are assigning labels here, let's call this the z-axis, the bond axis is the z, and then we have the x and the y. So we have the 2px orbitals and the 2py orbitals that can interact. And notice that their interactions look the same because they're basically the same orbitals, just in different planes. So they look exactly the same. They have the same energies, that's degenerate. So these orbitals in the pi set, there's two orbitals that are equal in energy. We call those degenerate orbitals. And then we get the pi bonding and the pi star anti-bonding. And right off the bat, we can actually, let's do O2, because that's almost the whole point of this, is to see why is O2 kind of peculiar in having unpaired electrons. Well, think about having an oxygen atom over here and then an O atom over here, so we can make an O2 in the middle. And so oxygen is a 2s2, 2p4, so 2s2, 2p4. So we're just picturing an O atom on the outside of the molecule. And this almost doesn't matter that much because I really want to understand what's in the middle. But if I'm just understanding, I'm taking an O atom here, an O atom here, thinking about those orbitals overlapping with each other, the bonding model's in the middle. So I'm just putting the total of let me use a pointer here. So 2, 4, 6, 8, 10, 12 electrons into this diagram, but in order of low to high energy. So our axis here is energy is increasing towards the top. So I'm going to fill my electrons in starting at the bottom. So going 2, 4, 6, 8. So I still follow Hund's rule in the degenerate orbital. So that's 8, 10, and then my last two, boom, spin paired. They're paired in the same direction. That's where I get unpaired electrons for O2, is just by the construction of this orbital and seeing that it's really a complicated picture of bonds and anti-bonds canceling each other out. And the picture of the bond is not as simple as we thought from the hybrid orbital theory or from our Lewis structure. Now let's think about the net bond order for O2. So if we're going to calculate the bond order, so the bond order should be equal to 1/2 the total number of bonding electrons. Well, let me circle the bonding electrons in red. So these are bonding, and then all of these are bonding. And then the anti-bonding orbitals are here within the structure that has electrons in those orbitals. And so we have a total of 8 electrons in bonding orbitals, but then I have a total of 4 electrons in anti-bonding orbitals. So I have 1, 2, 3, 4 bonding orbitals. You see how that still ends up being a bond order of 2. So my bond order for O2 is still double. So I still get a double bond. That's not the wrong picture for O2. It's just I'm seeing a complicated picture of what it means to be a bonding versus an anti-bonding electron. If you were to say this is kind of complicated, what is the net bond? The net bond for O2 is, it's kind of like it has a sigma bond. That's this bond here. So it has that sigma bond between the 2p orbitals. And then it has like one electron net in a pi bond in one plane, and then a net electron in a pi bond in the other plane. And that those are just canceled out by their anti-bonding electrons. So I have like the one electron that's kind of net bonding in each of those orbitals. So you see how it's a really complicated picture. It's not like there's, in most of the other cases of pi bonding, we had like 2 electrons in one pi orbital. This has like one net in one pi bond, and then another net in the other pi bond, 90 degrees, bisecting the plane of that one bond. So complicated picture, but really simple, like falls out really easily from this theory on why oxygen has unpaired electrons. But you see the idea of what sigma bonds are and what pi bonds are exactly the same. We're just seeing that pi bonds are planar bonds. Sigma bonds are bonds symmetric. They're like symmetrical about the bond axis of the molecule. And so you see that the idea that this is a planar type bond and that this is a like linear type bond. Now, let's take a look at something from left to right that happens that's kind of peculiar. I don't know if we would have expected this, but if we're looking at the bonding orbitals, that from left to right, there's a big change actually in the sigma 2p energy. That if you're looking at lithium-2 and diberyllium, it almost doesn't matter because they're really not using the 2p set anyways. If you're looking at lithium-2 and diberyllium, if we go back to these two, they were just bonding between the 2s and the sigma 2s and the sigma 2s star. And so these are looking at just the middle pictures. These aren't looking at the atoms making the orbitals. And so if I'm looking at lithium, this is just putting for lithium-2, how many valence electrons does that molecule have? And the valence electrons for lithium-2 is just 2, so we're putting 2 electrons in for lithium-2. If we're at diberyllium, then we're putting 4 electrons in because there's 4 valence electrons. So we're just looking at the valence shell orbitals, so the valence electrons, and so we're just filling 4 electrons in here. So we have a net bond order of, like we saw for lithium, of a single bond, for beryllium-2 of 0. So because we're just putting 2 into a sigma, 2 into a sigma star for diberyllium. We're neglecting for those the 1s overlaps, but we're just focusing here on the valence shell orbitals. And if I go across to B2, then we're putting for B2, we have 6 valence electrons that go in because each boron has 3 valence electrons. And so we go 2, 4, and then 6. And so diboron's kind of interesting in that it has a net single bond. So the bond order of B2 should be a half. It has 4 bonding electrons, 2 anti-bonding electrons. Its bond order is 1. But it's not really like usually you think a single bond. If I'm picturing boron, like it kind of says that this is probably its best Lewis structure that would be consistent with the MO diagram of a single bond. But that single bond's really not a sigma in this case. It's really, one of them looks like this orbital with 1 electron, and the other one has the p orbital sticking straight out of the page with 1 electron, because it's putting 1 electron into each of its pi bonds. And then if we were to look at the, is it paramagnetic or diamagnetic? Basically, does it have unpaired electrons, paramagnetic, or does it have 0 unpaired electrons and is diamagnetic? It would be diamagnetic for lithium-2. I'm going to put this in parentheses that beryllium-2 doesn't really exist, but if it did, it would be diamagnetic. Then B2 would be paramagnetic, meaning it has unpaired electrons. C2, just put 2 more electrons in. So for C2, and this is kind of an interesting question too, because if you're picturing carbon that has 4 valence electrons, why not just pair them all up for some sort of crazy quadruple bond? In fact, you can find sources online that will say, oh, there's a quadruple bond between 2 carbons. And I think it's completely fiction though, because if you're picturing the diagram you get for C2, just picture for C2 that we have 8 electrons going in, and so 2, 4, 6, 8, and let's make sure that we're, that we see that these orbitals here, these are the anti-bonding orbitals that we're thus far filling in that are anti-bonding electrons. And so that those electrons aren't pulling the nuclei together, they're trying to break the bond that we're trying to make. And so for C2, our bond order is only going to be 2. So for C2, the bond order here would be a half. We get 6 bonding electrons, 2 anti-bonding electrons, so that bond order is only 2. So we get a double bond between 2 carbons, but all of our electrons go back to spin paired for diamagnetic. So we have, interestingly, between 2 carbon, 2 pi bonds would be the best description. So the best description for carbon would look something like this, where that's actually not a sigma and a pi. We probably never asked this, but the bonding nature here would be that this is 2 pi bonds and not a sigma and a pi, from what we can more clearly see with MO theory. Now, to go back to hybrid theory, our double bonds within hybrid theory are still best described as a double is a sigma and a pi, a triple is a sigma and 2 pi, and within most of the molecules that we're describing, if you look at ethylene like we did earlier, it really does have the description. If you look at MO theory more closely for bigger molecules, we're only going to look at diatomics in this chapter, but if you were to look at MO theory, you really support most of the description of those pi bonds and the sigma bonding nature within those molecules within like a MO type picture. So for C2, now we can also do ions. We could also look at another example could be, well, what about C22 minus? That's actually the carbide ion. It's actually a fairly stable anion. And so the C22 minus ion just has 8 electrons going in plus 2. So it has 10 electrons in the diagram. So we just put 2 more electrons into the diagram. And then it ends up having a triple bond. And so C22 minus ends up looking like this. And that's actually a Lewis structure that we probably would have wrote with a triple bond, 2 lone pairs. And then within C22 minus, we have a bond order of 8 minus 2 antibonding for 3. So because we have bonding, antibonding in every one of our diagrams, the biggest bond we can ever get within MO theory for these diatomic molecules is 3. We're never going to get to a bond order of 4 because we always have this antibonding orbital in the way. And we have to fill electrons from low to high energy. So for N2 is energetically equivalent or electron count equivalent to the C22 minus ion, 2 times 5, 10 electrons. So that same diagram that we just had for C2. So triple bond here. So our bond order would be 3 for N2. And then it would be paramagnetic. Or not paramagnetic, diamagnetic. All its electrons are spin paired. Then we get to O2. O2 is that paramagnetic one. We did this earlier. But now it turns out that this orbital set here, the sigma 2px, why is it so sensitive? Why is it starting off higher than the pi set and then dropping lower? The answer is complicated. I think it has a lot to do with we are already putting 2 electrons in terms of s orbitals between nuclei that aren't particularly electronegative, that don't really have the electropositivity to pull the electrons into that region. So we have to go from left to right to get to like O2 and F2 to get to electronegative atoms that have a pull for more electrons between their nuclei. But you'll see in a moment that we'll give you base diagrams for the final exam, so you don't have to memorize this artifact or this detail. That for O2, we're going to fill its 12 electrons in. So we're going to fill 2, 4, then we're going to fill the sigma 2px next, then the pi set, that's through 10, and then finally arriving at the pi star 2p, and then going back to the bond order of 2 for O2, but paramagnetic. And this being really the key detail, that O2 being paramagnetic and being supported by this model is a big win for molecular orbital theory. And again, I think this is the primary reason we're talking about MO theory. You can do ions of any of these structures. You can add electrons, remove electrons, like peroxide or superoxide ions are common ions of O2. Let's take a look at an example here of the peroxide ion. So if we're just putting then 14 electrons in to O22 minus, let's go back to a different color. So we're going to fill in for O22 minus 2 more electrons, spin pair. So we now come up with a spin paired molecule that's diamagnetic, no unpaired electrons, and then has a bond order of 1. So O22 minus looks exactly like you would have thought. So within MO theory, what you're getting is maybe a description that lone pairs really aren't so much lone pairs as they're the result of bond making versus breaking, averaging out. So if we try to make a bond and then we try to break the bond with the antibonding orbital, that just ends up being like lone pairs. So lone pairs are just the averaging effect of trying to make a bond versus then trying to break the bond. And so we end up with lone pairs here around O22 minus. F2 looks very much the same. F2, 14 electrons, just like O22 minus, so the same basic diagram for a single bond. Diamagnetic in terms of its electrical behavior, and then neon 2 back to something that shouldn't exist. So once we go back to neon 2, if it were to exist, would have 16 electrons. So 2, 4, 6, 8, 10, 12, 14, 16. And so we're now back down to a bond order of 0, 8 minus 8, times a half. And then you can put di in parentheses. And again, just thinking it doesn't really exist, but if it did, we would expect that it wouldn't have unpaired electrons. And so just putting kind of a star on these as unstable. Now, when we say unstable, I mean unstable that it shouldn't really exist for any finite period of time. Even if something is quote unquote stable, doesn't mean it will exist for a long time. So like lithium-2 as a diatomic molecule probably isn't very stable, but it's stable enough that it should be able to exist, that we could detect it and get its properties. So that's what we mean that by unstable, just that it shouldn't really ever exist for even a short period of time. All right, let's pause here for our quiz. Okay, again, the keyword's Faraday if you were going straight to the link. In case anybody was still jotting anything down, I just went ahead and came back to the slide here. Again, I post the PDF, so if you feel like you were quickly writing, if there's something you may have missed here, I have been posting the PDF copies of all the slides so far. But that's kind of a quick summary so far. Now, this diagram here also kind of showing you what I was filling into the previous page, just kind of picturing these two orbitals here. For B2, C2, N2, the pi set come next in energy, and then these orbitals invert. And it's really more, this diagram doesn't show it really clearly, it's really the sigma 2p that are lowering in energy. The pi set from left to right doesn't really so much change in energy as the sigma 2p is just lowering in energy. But then we're filling into the sigma 2p next, and then the pi 2p afterwards with electrons. And just filling in, getting our bond order increasing from B2 to C2 to N2, and then from O2, F2 to neon 2, then decreasing in bond order. So we're going single, double, triple for B2, C2 to N2. Now, N2, if you're thinking just of atomic radius, so just think of the atomic radius of boron, carbon, nitrogen, oxygen, fluorine, and neon. So the atomic radius, just left to right trends of their size from chapter 7. And so we should have a decrease in size from left to right. So boron should be bigger than carbon, bigger than nitrogen, bigger than oxygen, bigger than fluorine, bigger than neon in terms of the size of these atoms. And so then if you're pairing up like two nitrogens compared to two borons, two nitrogens has two good things going for it to be a short bond. One is that it's just smaller than boron, and the other is it's a triple bond. And so you notice here the N2 bond is really short compared to the B2 bond, particularly long. And that's just a virtue of boron's a bigger atom, and it's also a single bond. So we have a couple things going here where single bonds are shorter than, single bonds are longer than double bonds, which are longer than triple bonds in terms of length. And then also the strength inverts. So in terms of strength, the triple bond is stronger than the double, stronger than the single. So single bonds longer and weaker, triple bonds shorter and stronger. And so you can see that working out here, that boron has a particularly weak bond, and then the nitrogen bond, really strong. So 290 kJs per mole for diboron, 941, so about more than three times greater for the N2 bond with its triple bond. And so then you can then see this trend invert where oxygen so it's a shorter bond because it's a double bond. So O is smaller than nitrogen as a atom, but the O2 bond length is longer than the N2 bond length because we go back to being a double bond. So within the same row of the periodic table, generally if you're comparing atoms in the same row as each other, generally any of the double bonds will be shorter than any of the single bonds, and then the double bond should be longer though than the triple bonds. Or in other words, the triple bond should be shorter than the double bonds. So as long as you're comparing N2 and O2 because you're in the same row, N2 being triple should be shorter than the double O2, meaning even though O is smaller than N as an ordinary atom, once you make the double bond versus a triple bond, the N2 bond is shorter. And then F2 continues the trend. Even though fluorine is smaller than oxygen, F2 is longer than O2 because it's a single bond. So it just kind of means that for left to right trends, that you can just really rank single versus double versus triple in the same row of the periodic table as each other and not really worry so much about the relative atomic radius size. Now, if you're then comparing O2 and C2, this is an interesting comparison here because O2 and C2 are both double bonds. Because they're both double bonds, you can then say, oh, well, oxygen is smaller, should be shorter. So the O2 double bond should be shorter than the carbon-carbon double bond. And let's see if that works out, and that is true. So 1.21 angstrom versus 1.31 angstrom. Now, interestingly, the oxygen bond, even though it's shorter, ended up being weaker, but let's not get into necessarily every comparison. But if you notice here, the O2 bond is actually a little bit weaker than the C2 bond. So there is a little bit of a complicatedness of bond strength as you compare from left to right, but as long as you look at the bond length, you can see that triple bonds in the same row will always be shorter than double bonds, always shorter than single bonds. If you look at fluorine versus boron, so if we were to compare B2 and F2, they're both single bonds, but fluorine's smaller, should be shorter, and it is. And then boron is longer as a result of it being a bigger atom. So you can make some comparisons between the bond length just based on what you know about the atoms or what you know about their bond types in these comparisons. And so what we're seeing here also is that you get the proper picture within MO theory of whether or not the electrons should be spin paired and diamagnetic. So diamagnetism is the result of all electrons in every orbital being spin paired. The spin paired nature, if you imagine H2 has electrons almost like spinning around the molecule with like a net spin, that if you apply a magnetic field, that you actually get a repulsion of the molecule with the magnetic field. So you get a weak repulsion of the diamagnetic molecules with a magnetic field. So you may have thought that molecules that are diamagnetic would have no impact by a magnetic field, but they actually have a weak repulsion, and just due to all the net spins that those electrons have, even though they're net spin neutral, they are still spinning, so that you get a repulsion, but weakly from a magnetic field. But paramagnetic, if you took something with net electrons, what happens is O2 would be pulled into a magnetic field. So oxygen can be pulled into a magnetic field due to its net spin that the molecule has, due to having unpaired electrons. And then I don't think I focused on it so much in the here, like in the opening picture of this, where we had the side of O2 with unpaired electrons. That was the O2 molecule being pulled into a magnetic field. So you can actually, maybe I'll post a video where you can actually do this demo. Just have a magnet take liquid oxygen, and you can see the oxygen's being pulled into the magnetic field. So you can clearly see with your eyes that oxygen truly is paramagnetic and has unpaired electrons. Pictures. And then I think what we'll finish up on today is just the idea that for exams, you get these base models here where what we expect that you know is like you can apply that these should be the 2s orbitals, these should be the 2p orbitals. These are inverting the order of this orbital here, so you're getting the relative energy in between. So you have to be able to understand that we have the 2s and the 2p interacting. You're getting the sigma 2s, sigma star 2s order here, then it's the sigma 2p. Then because there's two, I know that's the pi set. The pi's are doubly degenerate, so I get the pi 2p, therefore the pi star 2p, and then the sigma star 2p. So I can assign these orbitals in both of the diagrams. I can put electrons in. I'll just do this last example here, even though we did this earlier. This is just 2 times 4 plus 2, but going into the proper diagram for C2. So we're just putting 10 electrons in here, 2, 4, 6, 8, 10. And then you can answer questions here like it's diamagnetic triple bond that we answered earlier. So you get the bond order of 3, and then it's diamagnetic. All electrons spin paired. Okay, so you get these base diagrams to fill into on like an exam, so you don't have to memorize the artifacts of the MO diagrams. So it's just all about filling electrons, assigning orbitals, seeing if it's unpaired or not, and then calculating bond orders, and then maybe answering questions about what orbitals are you filling electrons into? Like, what is this orbital here? It's like, oh, that's a sigma 2p. Or what's this orbital? It's a pi 2p. Okay, guys, that'll do us for today. Thanks for attending today. Good luck on the exam tomorrow, and I'll see you back here on Wednesday.